I will start. Okay, for those who are here. Okay, I think currently no one here. I think. Okay, let me check. Okay, it's okay. We will start now. Okay, those will they will join later. It's okay. Now, this is going to be we are going to have go through paper 4. Okay, which is going to be March 2021. Okay, so the paper 2021 March paper. We only have one variant, so this is going to be paper 4.2. Okay, so let's begin. So the first question over here is, okay, they ask you, okay, the most common oxidation state of cobalt, okay, is given, okay, which is going to be +2 and +3. So complete the electronic configuration of the following free ions. So if you look over there, okay, if you want to actually write down the electronic configuration, okay, so for chromium, okay, you can see, okay, for cobalt, sorry. So for cobalt, okay, you can see that they are going to be 4s2. Okay, I will just write down over here 4s2, and then 3d 1, 2, 3, 4, 5, 6, 7. Okay, so 3d7. So if you write them down, yeah, so it's going to be 4s2, 3d7. When you remove the electron, okay, from the cobalt, okay, let's say, for example, you want to remove the 2 electrons, we remove the 2 electrons from the 4s orbital. So the moment we remove from 4s orbital, this is going to become 4s0, and you are going to get 3d7. So you can write down like this, okay? Or you don't want to write down the 4s0, you just want to write down 3d7, it's okay. Yeah. And then if you remove 3 electrons, so you see here, okay, you want to remove the 3 electrons. 2 electrons is removed from 4s, and another one more electron is removed from d orbital. So you are going to get 4s0, 3d6. So you write down 4s0, 3d6. Okay. Now the next is going to be, if you have, okay, cobalt 2 plus, okay, and cobalt 3 plus, okay, both of them, okay, they form complexes, okay, with EDTA. Yeah. So the half equations, okay, are shown, okay, in the table below. Okay. So here they want you to use the table to predict what happened, if anything. Yeah. When separate aqueous solution of cobalt 3 plus and cobalt EDTA are left to stand in air. Okay, so what will happen? Okay, you are going to have, okay, let's say for example now, okay, I have aqueous solution of cobalt 3 plus. Okay, so if you have aqueous solution, okay, of cobalt 3 plus, which is this one, okay, when I am going to react, okay, left to stand in air. Now in air maybe contains oxygen. So for example, let's say I'm going to try to use this. Okay, you see, okay, cobalt, okay, 3 plus is going to be 1.82. Okay, see, this 1.82, okay, they will go over here. Yeah, so if you follow here, they are going to actually come over here. Yeah, so in this case, okay, you will see that, oh, we thought that oxygen is going to react. But now, okay, because of this is more positive, water is reacting. Then it doesn't make sense. Actually, it makes sense, okay, because if you leave it in air, okay, air also contains water vapor. Yeah, so it makes sense. Doesn't mean that air must be always oxygen. Okay, so in this case, okay, when you put them there, okay, what will happen? Okay, cobalt 3 plus, okay, plus electron, they will form cobalt 2 plus, 1.82. So this one is going to be more less number than 1.82. So they are going to give you 2H2O to give you oxygen plus 4H plus and 4 electron, okay, which is going to be negative 1.23. Okay, so if you want to calculate, okay, what is going to be the E value, which is this reaction is feasible. Okay, so 1.82 you minus with 1.23, this is 9. This is going to be 0.59. So positive 0.59 is going to be the E value. Okay, so what will happen? Okay, the reaction is going to, you are going to produce, okay, oxygen gas. Okay, from here I can see oxygen gas is produced. Okay, it's produced. So predict what happens. Okay, the reaction you can actually say, okay, rather apart from just writing like this, okay, CO, you can say that CO3 plus, okay, what CO3 plus is doing, okay, it is going to make water to release electron. Okay, when it is releasing electron, this is going to oxidize water. Yeah, so CO3 plus is or will, okay, will oxidize water to give oxygen gas. Okay, CO3 plus, okay, changes into CO2 plus. You can write down that. Yeah. Now, and if you want, you can also include the E value. Okay, the E cell. Okay, the E value is going to be positive 0.59, which is going to be feasible. Okay. Now, if let's say you are using the aqueous solution, okay, of cobalt EDTA, okay, so if you are using that, okay, what will happen? Okay, so if I have, okay, this, okay, and I am going to use, okay, cobalt 3 plus, okay, so I'll erase this part first. Now, if I use cobalt 3 plus, okay, aqueous solution of cobalt 3 plus, okay. Now, if I do this, okay, you can see that, okay, you know that cobalt 3 plus, okay, if you compare between these two, Okay, we know that this is going to actually move forward. Okay, this is going to move forward, and then okay, we know that okay, this is going to be 0.38. They are going to move over here. Okay, in this case, okay, it is not like what we want. Yeah, it's not like what we want. We want okay, COEDTA minus to react, but in this case, COEDTA 2 minus is going to give you this. So in that case, we have to make some adjustment. Yeah, what is the adjustment? Okay, we cannot use okay, this equation. Okay, try to change the equation, but you still going to use okay, this particular equation. Now, this particular equation okay, is going to come in handy. Okay, which is going to be okay, when you put okay, this cobalt 2 plus, okay, now you compare. Okay, if you have this, okay, and then you react, okay, so what happens, okay, this is more positive, 0.38 is more positive, like what we want, okay, COEDTA minus is reacting, and this is going to actually go and produce this, okay, so which is going to produce CO2 plus, okay. So in this case, okay, what we need to look at is, okay, let's hold on, yeah, copper 2 plus and cobalt 3 plus, use the data when separate aqueous solutions of okay, these are left to stand in air. Yeah, sorry, I think this one no need. Okay, I made a mistake then. Okay, no need to compare with this. Okay, they are comparing. Okay, they are comparing leaving these two in air. Yeah, leaving these two in air. So here, okay, I can see that okay, this is going to be moving forward. Okay, 1.23. Okay, and then okay, this is going to move backward. Okay, so okay, that is going to move backward. Okay, okay, let me check. Okay, now okay, let me continue again. Now, okay, we are going to predict okay, when separate aqueous solution of cobalt 3 plus and cobalt EDTA minus are left to stand in air. Okay, so now, okay, I'm just going to try to predict over here. Okay, let me actually bring the marking key also to help. Okay, now, so here, okay, I'm going to actually look at okay, the reaction with air. Okay, the moment I have the reaction with air, okay, now okay, I know that I need to focus on these two equations, okay, these two half equations, and when I focus on here, okay, I know that this is going to move forward, okay, 1.23 is going to move forward, and the one that is going to move backward is going to be this one. Okay, but you can see that we want okay, these to be reacting. So in this case, it doesn't make sense. It doesn't react, yeah, like what we want. Okay, COEDTA 2 minus is going to change into this, but we want this to change. So therefore, okay, this reaction, okay, there will be no change or no reaction. Okay, no reaction. Okay, so here, okay, when they ask you to predict what happens or what is going to be seen, let's say, for example, later they are going to ask you, okay, what is going to be seen? Okay, let's check. Okay, 1A, 1B, okay, B is going to be, yeah, they are mentioning about, okay, CO3 plus is going to be reduced to CO2 2 plus, which is correct. Oxygen is going to be produced, okay, and then this is going to be greater, feasible, okay, no change, okay, not feasible, okay, done, yeah. So Next question, okay, is going to be, they are asking about C, yeah. C is going to be, they are telling that hydrated cobalt 2 nitrate, okay, is going to be a red solid that behaves like hydrated magnesium nitrate, yeah, when heated. So describe in detail what would you expect, okay, when you have crystals of this heated in a boiling tube. First gently, okay, and then more strongly. If you heat gently, first what is going to happen, you are going to remove the water, okay, the hydrated compound, you are going to get water, so water is going to be released, yeah. So what is going to be observed, so you are going to observe, okay, droplets of water, yeah, or steam, okay. So you are going to actually have steam evolve because you're using a test tube, okay. So you are going to have, okay, either droplets, okay, of water, okay, at the top of the tube, or you can mention steam, okay, is evolve, okay. So you can see condensation and then steam is evolved, and we know after that, okay, when you heat them strongly, then only you are going to have decomposition. So the decomposition is going to be, you are going to get nitrogen dioxide, okay, and then oxygen, okay. Since they didn't ask you to balance, in this case I didn't take okay, I didn't balance it, but if you want also can balance very fast, yeah. So this is balanced, and you can see here, okay, what you are getting over here is going to be, you are going to get cobalt oxide, okay, cobalt oxide, NO2. NO2 is a brown gas, so you can describe, okay, brown gas is evolved, okay. And then there is another gas which is oxygen. You can actually test this gas, okay, by using glowing wooden splint. So it a gas, okay, that relights, okay, relights a glowing wooden splint, okay, will be formed, okay. And another one is going to be, maybe you can also mention that, okay, this is a hydrated compound. Hydrated compound is a red solid. So the moment when you heat gently, okay, when water is released, you are going to get a nitrate compound, yeah. A nitrate compound, okay, all nitrate compounds, they are soluble, yeah. So you can see that the nitrate compound over here that is going to be formed, they should be soluble as well. So you can also mention that the red solid, okay, dissolves, okay, or you can say the red solid dissolves or turns into liquid, okay. You can see all the observation that you expect, okay, over here, yeah. Now explain why the thermal stability of group 2 nitrates increases down the group. Now thermal stability, okay, we know that, okay, for both carbonates and for nitrates, the thermal stability are going to increase down the group. Now this is because, okay, as you go down the group 2, the cationic, yeah, the ionic radius, okay, ionic radius, okay, decreases down the group. And we are talking about the cation, okay, the metal group 2, yeah, down the group 2, okay. Now once this is happening, okay, we can say that, okay, this is going to reduce the charge density, okay. So charge density is going to be affected by charge divided by radius. So the charge density is going to be decreasing. So the polarizing power, okay, is going to be decreasing, okay. Polarizing power of the cation, okay, is going to decrease. Therefore, okay, they are going to become less polarizing, okay, or they are going to distort, okay, or they say, okay, the cation will have less distortion, okay, will have less distortion towards the electron cloud, okay, around NO3 ion, okay. So therefore, okay, therefore there is no distortion. So the bonds of nitrogen and oxygen in NO3 minus are less, okay, weakened, and requires more, okay, more heat to be broken, okay, or more energy to be broken. Okay, next, okay. So the next part is going to be the question number 2. So you have, okay, iron 2 compounds are generally only stable in neutral, non-oxidizing conditions, okay. So it is difficult, okay, to determine, okay, the lattice energy of FeO experimentally. So they are asking you to use the data from the data booklet, okay, and using this Born-Haber cycle to calculate the lattice energy. Now, I have taken the information from the data booklet for you. What is the information required? It's going to be, you need to know the bond energy, okay, to break the oxygen double bond oxygen, yeah, the O2, yeah, so that we can use that information, okay, for the atomization of oxygen. Okay, and then we also need information, okay, whenever you can see Fe is going to change into Fe plus, then after that you can see Fe2 plus. It means this is going to be first ionization energy and second ionization energy. All these are available in the data booklet. But do remember the new syllabus, okay, they are going to provide the information that you required in the paper itself. So no need to worry about that. Now I provide for you here. So let's actually try to solve this, okay. So here, okay, you are going to have, okay, here you can see Fe solid to become gas. That is going to be enthalpy of atomization of Fe. So now you can see half O2 to become O, yeah. So it's going to become 1. So here we know if you use 496, you are going to change O2 to become 2O, which is 496. I want only 1O. So what you need to do, you need to divide by 2 or you times by half, yeah. So that is going to be, you are going to get 496 divided by 2 is going to be 248, yeah. So it's going to be, I'm going to just write down 248. Okay, positive 2.248, okay, because it's going to be endothermic, okay, to break the bonds, okay. So once you have that, okay, atomization is settled. Now this part is going to be your first ionization energy of Fe. So first ionization energy is going to be plus 762, done, yeah. Second ionization of Fe, yeah, to give you Fe2 plus. So the second ionization energy, I have already taken the information, is done, yeah. And this is going to be first electron affinity, yeah, of oxygen to give you O minus, and then this is the second electron affinity of oxygen. So always remember the first electron affinity is always going to be negative, yeah. You are trying to bring the electron and trying to form the bond, yeah, to form the bond. And because it's going to be formation of bond, it's going to be electron is negatively charged, and then generally the nucleus, yeah, is going to be a lot of protons are positively charged. It's going to be formation of bond. But as you once you get the O minus, okay, when you try to bring in another electron, now it's going to be repulsion is going to happen because negative charge and then the electron is negatively charged. So when you do that, you need to overcome the repulsion. So you need to actually give energy to overcome that repulsion. So the energy is going to become positive. That's they can ask you about this. Yeah. Now, once you have this, okay, you just need to solve, okay, this, okay, like for example, clockwise equals to anti-clockwise, okay. So if I put this, okay, if I want to calculate, okay, 416, okay, clockwise plus 248 plus 762, okay, plus, okay, 1560, okay. If I normally what I do, I will combine these two, okay, to find out, yeah, whether it's going up or going down, yeah. So here is 798, okay, and then it's going to be negative 141. So I will have, okay, a positive value which is going to be 657, yeah. So positive 657, which is going to go up, yeah. So I'll just put clockwise, okay. So 657. And then this is the lattice energy. You can see it's coming down, which is going to be clockwise also, plus lattice energy. And you can see once it comes over here, this is going to be anti-clockwise. So this is going to be negative 272. Okay, what you need to do, you just need to find the lattice energy. Lattice energy is going to be negative 272. Okay, you minus 416 minus 248 minus 762 minus 1560 minus 657, and then okay, you will get the answer. Yeah. So once you do all this, okay, the lattice energy, you will end up having negative 3915 okay, kilojoule okay, per mole. Okay, so you just need to write down. Yeah. So if you look at the marking key also, okay, you see negative 272. Yeah, negative 272. We have 416. Okay, 416. Half of 496 done. Okay, 762 correct. 1560 correct. Okay, and then this one, if you join, you will get 657 and plus lattice energy. So our answer must be correct. Yeah, unless okay, I didn't calculate properly or I make mistake over here. But okay, final answer, you should get negative 3915. Lattice energy is always going to be negative. Yeah. So okay, thank you, Ashley. Okay, no problem. Okay, now, so most naturally occurring samples okay, of iron 2 oxide are found as the mineral this wustite mineral. Yeah, so this wustite has a formula okay, which is going to be Fe20OX. It contains Fe2 plus and Fe3 plus ions. Now they have mentioned that okay, 90% of the ion present is going to be Fe2 plus and 10% is going to be Fe3 plus. So how we do this, okay, if you want to find out the total charge and so on, it's quite simple, okay, but you need to think outside of the box over here, okay, because okay, we know that okay, whatever charge that you have over here, okay, for Fe, okay, must be okay, it's going to be the same charge over here, which is going to give you the neutral molecule, which is going to be 0. So if you look over here, 20 okay, must be times with the charge, but normally we know the charge Fe whether it's +2 or +3, but because there is going to be a mixture over here, so we need to actually say 90% of it okay, is going to be +2. So I'll just put 2, okay, positive 2. Okay, and then 10% is going to be +3. So I just count, okay, okay, and then I have 20 of them, 20 atoms or 20 ions, yeah, and then okay, when I add with X, okay, X number, oxygen is always, no need to worry lah, oxygen is always -2, okay, X times -2. The charges of the entire XO and the charges of the entire 20 Fe that contains Fe2 plus and Fe3 plus, they will give you 0. Okay, so what you need to do is to calculate what is X. Yeah, so let's say for example you have okay, let's say in between of +2 and +3 over here, let's say 2.5 for example. So of course this one is going to be also -2.5. Yeah, so when you add them together, then it will become 0. Yeah, so let's actually do that. Okay, so I cancel this. Okay, this is 1, this is 5. I have 9/5. Okay, plus okay, this is going to be 3/10. Okay, and then -2x equals to 0, 20. So this is 18/10 plus 3/10. Okay, 20 minus 2x equals to 0. So this is 21/10 times 20. This one is 2x. Cancel, cancel. I get 42 equals to 2x. X is going to be 21. Okay, which is going to be, X is going to be a positive value over there. So X is 21. So it requires 21 atoms of oxygen, okay, to balance the charge between these two. Okay, now let's move forward. Now state and explain, okay, how the lattice energy of FeO compares to the lattice energy of CaO. Now, Fe is going to be 2 plus. You can see over here, Fe2 plus, okay, from the molecule here. And then you have Ca2 plus. Now, what you need to do, if you want to compare the lattice energy is dependent on the charge density, charge divided by radius. So the charge are the same, +2. So you cannot compare the charge. So the only thing that we need to look at is going to be the radius. So if you look at the radius, you can actually get the radius from the data booklet. I have actually taken it from the data booklet, and I have these two values. And from here, I can see that Fe2 plus is going to be having the ionic radius, which is going to be smaller. So I'll just write down Fe2 plus has smaller ionic radius, or smaller cationic radius. So because of that, the charge density is going to be greater, or higher, than Ca2 plus. That makes Fe2 plus to have they are going to have greater attraction. They are going to be able to attract more towards the oxygen. So you will have, it has greater attraction towards O2 minus, which makes, if you have more attraction, means more bond forming, which makes the lattice energy to become, lattice energy is always negative, so it become more negative, so it's going to be to become more negative, more bond formation, or you can say more exothermic than CaO. Done. So you can see it's more negative, smaller radius, higher charge density, greater attraction. If you want to include stronger ionic bonds, you can include stronger ionic bonds. Between what? Fe2 plus and O2 minus. Everything is there, in our answer. Now let's move on. Heating FeO results in the formation of Fe3O4 as shown. So that is going to be the reaction number 1. And then they say each formula unit of Fe3O4 contains 1 Fe2 plus and 2 Fe3 plus ions. Show how reaction 1 can be described as disproportionation reaction. So you can see, you just need to calculate the Fe over here, the Fe in FeO, is going to be, the oxidation number is going to be, this is -2, so this is +2. And then here, any neutral element, they will have the 0. So Fe is going to be 0. And then Fe in Fe3O4, you can calculate, 3 times X, plus 4 times -2. It's a neutral, so 0. 3X equals to 8. X is going to be 8/3. So it is going to be 8/3. The oxidation number plus 8/3. Now you can see that, the oxidation number from +2, it is going to actually give you, 1, this is more than 2, so you can see 1 is going to be oxidized, and another one, is going to be reduced, in this case, decrease in oxidation number. So the moment you just tell, what is going to happen over here, it's okay already, So, but actually no need to count this, they say that it contains 1 Fe2 plus and Fe3 plus. So you can actually just take it as Fe3 plus. So it is changing from +2 to become +3. So you can just mention about this. There is going to be both oxidation and reduction is taking place. In the same element is going to be oxidized and reduced. But do remember, you need to mention all this. So in this case, I am going to use +3, because they already mentioned. Now, Fe3O4 can be electrolyzed using inert electrodes to form Fe. Write half equation for the reaction that occurs at anode during the electrolysis of this. Now, if it is going to be anode, so you see this is a liquid, there is no water. There is no water, there is no hydroxide ions. So there is only O2 minus. So at anode, okay, we are talking about anions, okay, Fe2 plus, Fe3 plus, which is over here. Okay, they are going to be cations. Okay, so we are talking about oxygen over here, oxygen ions. Okay, so oxide ions. Yeah. So here, okay, write the half equation. What will happen? So you just write O2 minus. Okay, they supposed to lose electron. Yeah, to give you O2. So lose electron. So you write down plus electron, and then since this is going to be, you are dealing with 2 over here, so the charge on the left is -4. Okay, the charge on the right also must be the same, so you need to put 4. Yeah, so this is going to be the half equation. Yeah, now calculate the maximum mass, okay, of iron metal form, okay, when it is electrolyzed for 6 hours using a current of 50 ampere. Now, this one you need to be a little bit more careful, because the iron metal that we are going to have over here, it's involving Fe2 plus and Fe3 plus, slightly different than what we normally do. Yeah, but the first step is always going to be the same. Q equals to IT. Okay, Q is going to be the charge. Okay, I is going to be 50. Okay, time. Okay, it's going to be 6 hours. So 6 you change into seconds. Times 60 to change it into minute. Then times with 60 to change it into seconds. And you will have this number of columns over there. Now, we know, okay, they have mentioned, okay, so I'll just, rather than writing it again, I'll just make it bigger. Okay, this is going to be very important. We know that, okay, they mentioned that Fe3O4, okay, they contain, okay, 1 Fe2 plus and 2 Fe3 plus. Ignore the O4. Yeah. So once you have this, okay, we can actually write them down, okay, in terms of half equations. Then we can combine them. So you see, Fe2 plus, what will happen? Yeah. If you have Fe2 plus, it's going to be plus 2 electron. Then you are going to get Fe. If you have Fe3 plus, what will happen? So you will have Fe3 plus electron. Okay, and then I am going to plus 3 electron. Yeah, so 3 electron. Then I am going to have Fe. So this one I am going to try. Okay, okay, I'm going to try to get. Okay, hold on. Okay, they are going to use. Okay, they mentioned that it contains 2 Fe3 plus. Okay, therefore, okay, what I need to do is, I just need to put 2 Fe3 plus. Okay, so if you have 2, then everything must times by 2. So this is 6. Okay, and this is 2. Okay, so if you put them together, okay, in this particular molecule, okay, if you have the cation to be discharged, okay, you are going to get Fe2 plus and 2 Fe3 plus. This one and this one, you are not working into eliminating the electron. Yeah, do remember that. So 2 plus 6 is 8, and then you are going to get 3 moles of Fe. Now, what this will do, okay, we can actually use, okay, this information. Yeah, what is the information that is required over here? This is the information. Yeah, this particular molecule, okay, in order to be discharged, okay, to give you 3 moles of Fe, they require 4 moles of electrons. So, like what we have learned in the past, okay, 8 Faraday. Okay, if it is 1 mole of electron, then 1 Faraday. 8 Faraday requires 3. It is going to deposit 3 moles of Fe for this compound. So Fe, okay, if you find from the from your periodic table, Fe is 55.8. Yeah, so 55.8. I have the, okay, Fe is going to be 55.8. Okay, so we will use that. So once you have that 55.8, okay, so you just need to times, okay, so that you get the gram. Yeah, and you will okay, you will notice that, okay, this one also you can times 8. 1 Faraday is 96500 columns. Okay, so this is going to give you, okay, 167.4 gram if you calculate. Okay, now I can convert this to find out what is 1 columns. Yeah, so 167.4 divided by 8 times 96500. Okay, but I want, okay, for this amount of columns. Yeah, so what I do is going to be this value 167.4 divided by 8 times 96500. Okay, I times with 1080000. Yeah, once you do that, okay, you will get, okay, 234.19 gram. Okay, you can simplify this into three significant figures. You can just write down as 234 gram. Yeah, done. Yeah, next part. Okay, so if you have, okay, LiFePO4, okay, this is going to be used in lithium ion rechargeable batteries. Last time it is used to be very popular, yeah, but now, yeah, it's not in syllabus anymore. But do remember, okay, this paper is 2021, still new. Yeah, they can still ask you a little bit, okay, based on common sense. Yeah, so doesn't mean that they are out of the syllabus, they cannot ask at all. Yeah, so this is 1 mark. They are asking you, yeah, state one possible advantage of developing cells like lithium ion rechargeable batteries. Yeah, lithium ion rechargeable batteries, they are small, okay, and compact, and they are able to generate high voltage for that small or compact size. So that is going to be the answer. Now, they say that when the cell is discharging, yeah, so only this part not in syllabus, not the rest. Yeah, doesn't mean the rest is all in the syllabus. So you need to know. Yeah, so here, okay, they say when it is discharging, okay, this is going to be the equation, the half equations over there. So you need to find out what is going to be the change in oxidation state during discharging. And they say that, okay, for lithium, okay, what will happen to lithium? So for lithium, okay, let's actually find out what will happen. And then they say it's going to be at cathode. Yeah, so you just need to look at this. Okay, no need to look at the anode. Yeah, so this is very important when you read the question. Yeah, so Li plus, so it must be +1. Okay, just follow the charge. And then, okay, this one, okay, LiFePO4 4. Yeah, so this is going to be, okay, they are going to change, okay, into this. Okay, so we know that Li normally Li plus. Yeah, okay, so you have FePO4 minus. Okay, so that's the only way that this thing can exist. Yeah, so in this case, okay, there is no change, okay, in oxidation number. Okay, you can see here, okay, +1 to +1, no change. Okay, so if it is +2, then you are going to have a different value. Yeah, so in this case, how do I know this? Yeah, because I just take this one. Yeah, so if it is going to be neutral, then it's neutral 0. Yeah, so then if it is going to be -1, then it will combine with Li plus. Okay, if it is going to be different value, then it's going to be a different value over here. So in this case, okay, it's going to be always in this form. And also, if you want to remember, Li is always going to form, okay, it's a group 1 metal. Okay, they are always going to be Li plus. That is another way to remember. Yeah. Now the next part is going to be iron. Yeah, the iron over here. So we know phosphate is always PO4 3 minus. So iron is going to be, you just can write X plus -3 equals to 0. X equals to 3, +3. So +3. And then you can also find out from here Fe. Okay, if you want to just straight away use Li is +1 is okay, then plus X. Okay, PO4 is 3 minus, so -3 equals to 0. So X minus 2 equals to 0, X equals to +2. So you can just give your answer +2. Done. Yeah. Now write the overall equation for the overall reaction, okay, that happens during the cell is discharging. Now, when the cell is discharging, yeah, basically you are going to combine these two equations together. You see on the left, it's going to be electron. This is going to be electron. You just need to add them. Yeah, so no need to times. You just need to add. Okay, when you add them, okay, I will get something like this. Okay, which is going to be involving. There is going to be Li. Yeah, so I can see Li plus is there. Okay, on the left and the right. Okay, what I do, I don't leave it like that. Yeah, so I need to actually cancel this. This one and this one can be cancelled. Okay, so what the end, yeah, I'll just rewrite again and I write it as this. Yeah, so not only electron is going to be cancelled, we are also going to cancel the same ions. Yeah, or sometimes later you will see some examples. If you have same molecules, then you need to just need to minus or balance that part, yeah, bring to the other side, then it's going to be minus and so on. You can actually do that. Okay, later we'll see some examples like that. Now, iodates are compounds that contains, okay, this anion, yeah. So the anion is shown, explained with reference to qualitative model of electron pair repulsion. Why? Okay, this one is contains a pyramidal shape. Yeah, this one no need to go in detail. This is only one mark. Yeah, so if you have pyramidal shape, okay, pyramidal shape is going to be ammonia, right? Something the shape as ammonia. Yeah, so ammonia has 3 bonding pair, okay, and 1 lone pair. So in this case, if they are asking you, this one is going to be based on the qualitative model of electron pair repulsion. Okay, you can tell that, okay, this IO3 minus, okay, has 3 bonding pair of electron and 1 lone pair of electron. Okay, so you do not need, okay, to go in detail. Okay, but if you want to go in detail, yeah, of course you can actually look at the periodic table and you'll get something like this. Okay, 5s2, 4d10, 5p3. Okay, if you know, yeah, I think those good students, you know how to write all this. Okay, and we know that, okay, this part, okay, the p has 5 electrons. Okay, but you are going to require 3 electrons for bonding over here. Okay, so this is not enough space. They have to expand the octet. Yeah, so when they expand the octet, okay, so what happens? Okay, they are going to bring the 2 electrons somewhere here. Okay, when they bring the 2 electrons somewhere there, okay, you are going to form, okay, the 2. You are going to form bonding, okay, 3 bonding, okay, over here, 1, 2, 3, 3 bonding. So maybe they are going to form the 3 bonding over here, okay, and then, okay, these 2, okay, they are going to be involved for the pi bonding. Yeah, so that is going to be pi bonding, and we can see here this is going to be the lone pair. So if you're wondering, okay, from where suddenly I have 3 bonding pair, okay, I have 3 bonding pair from here, okay, this is the pi bonding, the 2 pi bonding, and this is the lone pair. Yeah, so this is for the the smarter kids. Yeah, so anyway, okay, if you are not sure also, it's okay, just this one is enough already. Yeah, now the reaction of iodine and hot aqueous sodium hydroxide is similar to chlorine and hot aqueous sodium hydroxide. Okay, so now, okay, you are going to actually you need to write the equation, okay, for the reaction, okay, of iodine, okay, and hot aqueous sodium hydroxide. Okay, so now, okay, we know, yeah, this is going to be a disproportionation reaction. Yeah, so just recall back. Yeah, so the reaction, okay, we have 2 types of reaction, okay, which is going to be if you are using it at hot and concentrated condition. Yeah, then you are going to have, okay, the reaction to give you NaCl and NaClO3. If you have cold condition, then it's only NaCl and NaClO. Okay, there is a way how to balance this as well. Okay, I'll try to show it here. Okay, so let's say, for example, okay, if I have Cl2, okay, plus NaOH, okay, I have NaCl. Okay, if it is hot condition, yeah, hot condition, you will have NaClO3. Okay, and then, okay, plus, okay, you are going to get H2O. Now, if it is going to be cold condition, you are going to get Cl2 plus NaOH. Okay, just simple, NaCl, NaClO plus H2O. Now, if you want to balance this, okay, you can actually use the oxidation number to help. Yeah. So here we know the oxidation number is 0. Oxidation number is 0. This is -1. This is also -1 for Cl. Yeah. And then this one, if you want to calculate, yeah, ClO3 minus, so X minus 3 times -2 is going to be -6 equals to -1. X is going to be +5. So this is going to be +5. And if you count over here, okay, x minus 2 equals to -1, yeah, and then x is going to be +1, okay. So I'll put +1. If you want to use, okay, this method, yeah, using redox reaction, yeah, oxidation number to balance, you see, from 0 to become +1, yeah. So what happens? 0 to +1, you are going to be +1, yeah. And then from 0 to -1, so it's basically -1. If the numbers are the same, yeah, basically we are talking about, okay, the number of moles, okay, no need to times, yeah. So this is always going to be 1, yeah. This is going to be always 1. This is going to be always 1. This is going to help us to balance the equation, yeah. So if this is same, no need to times, yeah. Then if you put that, okay, the next part is you are having 2Na, so I put 2Na over here. And then I also know that, okay, this is just an indication. So you see Cl and Cl, there's 2 Cl, so this is Cl2, is okay, no need to put. Okay, and then you check the oxygen, yeah, oxygen, I have 2 oxygen, I have 2 oxygen. Hydrogen, I have 2 hydrogen, I have 2 hydrogen. So I have already balanced. So I have Cl2 plus 2 NaOH, okay, to give you NaCl plus NaClO plus H2O. Done. But this one is cold condition, yeah. So now, okay, how do I apply this, okay, for this hot condition? Okay, for hot condition, yeah, so you can see this one from here to here is going to be -1, yeah, 0 to -1. So here, from here to here is going to be +5, 0 to 5 is +5. So it means that if you have this, there should be, this one should be times by 5. So that a -5 and +5, yeah. So you must times by 5. So it means that this is going to give us an indication. The 5, okay, can either come at here or here. Okay, this is just going to help us. Yeah, it's going to help us to put it where. Yeah, so here, okay, instead of putting the 5 over here, okay, I am going to put the 5 over. Okay, depends where you want to put. Okay, if you have memorized, then it's good. Okay, if you have memorized, you know that you need to put the 5 where. Yeah, so anyway, okay, here, okay, when I put left and right, normally, okay, when we balance, it's much more easier to leave the Cl2 or O2 and balance it towards the end. So here, I'm going to put the 5 over here, okay? If I put 5 over there, okay, I know that I have 6Na, yeah, 6Na, I put 6Na over here. Okay, the moment I put that, now, okay, I need to balance the Cl. That's why I told you, I leave the Cl towards the end, yeah? So you see, 5 and 1, 6. How to get 6? Easy, just put 3 over there, okay? And then now I just check, okay, whether my hydrogens are balanced or not. Okay, my hydrogen, 6 hydrogen, so I don't have, so I put 3 over there. So last is to look at the oxygen. So 3 oxygen and 3 oxygen, 6 oxygen, and I have 6 oxygen and it is balanced, okay? So this is how you balance, okay, using, okay, the oxidation number. So you see 3, 6, 5, 3, yeah? So 3, 6, 5, 3, yeah? So this is H2O, yeah? So you get that. So once you get that, okay, don't go and write your answer, the same answer over here, because they say it's iodine, yeah? So you just need to change a little bit, yeah? So you just put 3I2, okay, plus 6 NaOH. To remember, it's hot aqueous sodium hydroxide, yeah? So this one is going to give you 5 NaI, NaIO3, okay, plus 3 H2O. Okay, so you need to put that, yeah. So this is already okay, yeah. So hope you can remember how to balance using the redox, how to balance using oxidation number. Okay, I'll continue. Okay, now the decomposition of hydrogen peroxide is catalyzed by acidified IO3 minus, yeah. So this one is going to reduce, okay, this molecule as shown, yeah. So the reaction is going to be followed by this I2 by H2O2. So you have, okay, basically you are given all this information over here. So they, if you follow the question properly, they say that use the data to show the separate reactions of H2, okay, O2, okay, with IO3, and okay, after that with I2. Okay, it means they are talking about H2O2 with I2. Okay, and we need to show whether they are feasible or not, okay, under standard condition. That is the information. Do remember the first equation over here, it means that this is the catalyst. Okay, they say this is going to be catalyst and you are going to get I2. Then after that, okay, they say that the H2O2 will react with I2 and then the H2O2 will oxidize the I2. Okay, in that process, you're supposed to get this one back because it's catalyst. Yeah, later we'll write down all the information. So here, okay, the first thing is, okay, they say write, okay, separate reaction H2O2 with IO3. So I just put over here, and then I also put H2O2 with I2. Okay, I want to see whether the reaction is feasible or not. Yeah, if the reaction is feasible or not, yeah, you just have to check, yeah, using the E value. So H2O2, okay, H2O2. Now with IO3, this is IO3. Let's check. Okay, this is more positive than this. Okay, so this one will go to the right, and this is going to go to the left. Okay, so if this one is going to go to the left, okay, it doesn't make sense because, okay, this is going to the right, and then I2 is giving IO3. I want the IO3 to react. Yeah. So in this case, okay, is there any other option for me to try? Yeah, there is an option. Okay, instead of using the H2O2 over there at the top, you can try with this. Okay, let's try with this. Okay, so this equation. Okay, rather than using that. Okay, if you try these two, okay, you can see that, okay, this is more positive. This one will go to the right. Okay, this is negative. This one is going to go to the left. And you can see that H2O2 is reacting. This is the one reacting. So whether is it feasible? The answer is going to be this is feasible. Okay, but using which equation? These two equations. So you see IO3, okay, IO3 will oxidize. Why I say oxidize? Because this H2O2 is releasing electron. So releasing electron is going to be oxidation. So this IO3 will oxidize H2O2, okay, to O2, okay, with the E value of what? Okay, you see, this one, okay, is going to be 1.19. Go to the right. This is going to the left, so negative 0.68. So you get 0.51, which is feasible. Positive value means feasible. So in this process, what will happen? Since it's going to the right, or I2 is going to be formed too. So you can write down all that. Okay, let's actually look at the second one. Yeah. So if you look at the second one, okay, the second part, okay. Here, H2O2, we have two H2O2. Let's see which one we want to use, okay, and I2. Yeah, so you are going to react with I2. Now, let's say I take these two, okay, and then H2O2, you see, okay, this one, no problem, H2O2 is reacting. And then I2, less than this, so they will go here. So no need to think about another equation. So this is already, okay, valid, yeah, already valid. So I can say the E value, okay, is going to be 1.77. This one going to the left, so it's going to be negative 1.19. So if I count, it's going to be still 0.58, yeah, which is feasible also, yeah, feasible. Okay, but you need to tell, yeah, what will happen. This H2O2 will change into water, yeah, so water is being formed, yeah, but they are going to oxidize what? Oxidize what? They are going to oxidize I2 because I2 is losing the electron or giving out electron, yeah. If you forget about that, you just remember oil rig, yeah, oxidation is loss of electron. I2 is losing the electron, so it will oxidize I2 to produce this, okay, and during the process H2O is also formed, yeah, so it's done. Now, here they ask you to write the overall equation for the decomposition. Yeah, to write the overall equation, okay, it involves these two equations that we actually did just now. Yeah, so I have actually written it over here. Okay, I'll just enlarge this, and we will use this. Okay, now if you look at this, okay, this is maybe look a lot, yeah, but it's actually quite simple. Yeah, you see here, okay. I have written the the one that is 1.19. Okay, this is 1.19. This equation I have just simply written just like that. Yeah, just right like that I've written. And then I written the 0.68. Okay, this one. Okay, but I did it inverse it. Yeah, so it's going to go to the left. So I put like this. So what I did first is to eliminate the electron. Yeah, you see 5 electron, 2 electrons. So times by 2 times by 5 to get 10 electrons. So everything must times 2 and 5. Once you balance that, yeah, you will get something like this. Yeah, but I am not going to take that because I told you, okay, when you balance, you need to look closer, yeah, because there is 10 H plus, I have 12 H plus. I can simplify by bringing the 10 H plus to the left, so I have 2 H plus. Okay, I simplify. And then I also noticed that, okay, I what else, 5O2, 6H2O, all these are okay. So only that, yeah. So I have, okay, this particular reaction, okay, which we calculated just now. Okay, this one they don't want to find the E value, but this is what we calculated, 0.51. Yeah, so do the same thing. Okay, for this, okay, 1.77, this one. Okay, I just write down. Okay, and then I did for 1.19, which is going to be 3H2O plus half I2. Okay, so I just put over here. Do the same thing. You need to eliminate the electron. So times by 5 to get 10 electrons, times by 2 to get 10 electrons, then you can cancel. So once you do that, okay, you will have similar thing, yeah. But okay, you need to look closer also. You see 10H plus, okay, and 12H plus. You can bring to the right, and then you get 2H plus. Okay, simplify. Okay, then you can also see that there is 6H2O and 10H2O. You can bring the 6H2O to the right, and you can minus, and then you get the 4H2O. In total, you are going to get these two equations. Okay. Okay. Now, this one is actually the one that we did 0. plus 0.58. Okay, what you need to do now is going to combine these two. Yeah, so you just look closely what actually happens over here. They mentioned that, okay, this one, okay, reacting with 2iO3, okay, so 5H2O, O2 react, okay, this equation, yeah, so the one that they have written over there. So you can see, okay, it is reacting, okay, with this catalyst, okay, to form I2. And then they mentioned that the I2 is going to react with the H2O2 and proceed further, and it is reforming again the catalyst. Yeah, so that's why, okay, this is going to show the catalyst reaction. You react, okay, catalyst is helping, and after that they are going to reform again. Yeah, so you need to join them together because two of them are going to work together. So what I did, I used the red ink over there to join the two equations. Okay, so when I join the two equations, I simply add. Yeah, simply add. I will get all this. Okay, I simply added these two equations, and there are certain things that I can cancel. Yeah, which is going to be 2H plus, 2H plus I cancel. Okay, and then this one 5H2O2, 5H2O2, I have 10H2O2. I2 and I2 I can cancel also. Yeah, and then I have 10H2O, 5O2, that is the one that I keep. Okay, so the final answer that you're supposed to get from all these long equations is this one. And you can simplify that further also. Okay, 10 and 5, so you can divide by 5. Yeah, so you get 2H2O2 to give you 2H2O and then O2. Yeah, so this is going to be the overall equation that you will get, okay, for this reaction. Okay, so let's actually move forward. Okay, so the next part is going to be a student collects some data for the reaction of H2O2 with acidified IO3, okay, as shown in the table. So use the data to determine the order of the reaction with respect to all this. Yeah, so show your reasoning and so on. So if you look over here, okay, I'll erase first. Okay, so what we need to do is going to be sometimes, okay, you can do it easily, yeah, but sometimes, okay, you need to analyze a lot. Okay, in this case, okay, they want the H2O2, so I want the H2O2. I need to find, yeah, something that is going to be constant for these two. Yeah, so I can see the moment I see, yeah, I see this one is constant for these two. Maybe now I can use experiment 3 and 4. Yeah, because what happens, okay, for the experiment 3 and 4, I know that from here to here, okay, if I times something, yeah, in this case I think I times by 1.5, yeah, I can find out, okay, what is going to be this, yeah, what is the amount, because everything that I times, it depends on H2O2 only. So if you find out, yeah, you will find out that 8.82 divided by 5.88, it's also 1.5. So it means if you times by 1.5, then it's also times by 1.15. So this is going to be a first order. Yeah, it means if you times by 2, you get 2. Then it's first order. You times by 3, you get 3. It's first order. So this is going to be confirmed. Okay, H2O2 is going to be first order. Yeah, so you write down the reasoning. Yeah, and then okay, with respect to IO3. So let's erase this part. Okay, now we know that this is going to be first order. It will stay as first order. So now I want to find out IO3. Ideally, we want these two to be constant. So let's actually look at equations that I can use, the experiment that I can use, where both of them are constant. You see, I cannot use this one, yeah, for IO3 because it's the same. Maybe I can use 1, 3, 1, 4 or something, but I just check. Okay, if I use, for example, 1, 4, for example, yeah, 1, 4, I can use, okay, you can see here, it's the same, okay, but the problem is, okay, this one is not the same. So there is no other way, okay, you still need to use the H2O2. So what I did, okay, even I tried with another way also, which is going to be experiment 1 and 3. You see this one, when I times by 2, I know this is the same, okay, but this one, okay, I know this is also going to be times by 2. Yeah, there is 2. So how do I do that? So I know, okay, that H2O2 is going to be first order. So if it is going to be times 2, this one must be from here to here, must be times 2. And then there must be something over here, which is only dependent on IO3. So if I times by 2, okay, so what is this number? In order to find out that number, you need to find out 5.88 divided by 1.47. What will you get? Okay, and I get, okay, 4. Okay, so how do you get 4? 2 times what? 2 times 2. So if it is 2 times 2, okay, then of course, okay, this is going to be first order, 2 and then 2, 100% depending on this. Yeah, so I know that this is also first order, times by 2, times by 2, times by 3, times by 3. So that is going to be a confirmation of that being a first order. So I know this IO3 minus is also first order. Then, okay, I can actually use the whatever information that I have so far. I can also use that information, okay, to calculate for H plus. Okay, if you look at H plus, okay, H plus, let's see, okay, I can see that this one, okay, something like this. This is going to be double, okay, times by 2, and this is same, but this one is double. Let's use the same way. Okay, if this is double, so of course this one must be times by 2. Okay, then times with what? Yeah. So here, okay, what I notice here, when I times this by 2, okay, I just calculate 2.94 divided by 147. I get the value which is going to be 2. Yeah. So what is this value? If I times by 2, I get what? So this is 1. Okay. So what is 1? 1 is going to be 2 to the power of 0. Yeah, so it means that, okay, when I times by 2, 2 to the power of 0. Okay, when I times by 3, 3 to the power of 0. This is going to be a zero order reaction. Yeah, so this is going to be zero order to H plus. Okay, so this one zero order. So use your answer and write the rate equation for this reaction. Yeah, so K, okay, H2O2, okay, and then IO3 minus. I do not include the H plus because it's H zero order. Okay, so that is going to be my rate equation. Now, calculate the value of rate constant using the data from experiment 4. Yeah, so what you need to do, just use the experiment 4, all the data that you have over here. to find the K value. So I have actually put all the data. Just put the equation, yeah, and then find the K value. The K value is going to be rate. Okay, I took the rate and then find out the concentration from the table. You put over there and you find the K. You will get this. Okay, 4.2 times 10 negative 3, and then related to the unit. Yeah, so we know rate is going to be mole per dm cube per second. Yeah, and then we know this one is mole per dm cube, mole per dm cube. So it's mole per dm cube to the power of 2. So I can cancel 1. Okay, this is 1. Okay, so when I bring it up, it's going to be mole negative 1, dm negative 3. So bring up 3, maintain as negative 1. So that is going to be my my unit. Yeah, so let's actually move forward. Okay, for E. Okay, PbIO3 is only sparingly soluble in water at 25 degrees Celsius. Okay, so if you want to write the equation, then you write the equation like this. Okay, PbIO3 solid, okay, is going to sparingly soluble. So this one must be true, and this is the equation. So they are asking, yeah, the solubility product is given, okay, and then they ask you to write the expression for the solubility product. So KSP, what is KSP? So you do not include solid over there. So KSP is going to be Pb2 plus, okay, concentration, okay, and then this one IO3 minus, but make sure to put the 2 there. Okay, and we do not include this one, yeah, so which is going to be the solid, no need to include. Okay, and then that is KSP. Now calculate the solubility. For solubility, yeah, so we always use, okay, if it is 1 mole, then we say X. Okay, let's say 1 mole is X. So we know that, let's say whatever mole is minus X reactant. And then this is going to be double than that X, 2X. Okay, so that is solubility. Okay, we will use the term X. So if I put over here, you can just use the KSP value over there. So you see KSP 3.69 times 10 to the power of negative 13. Yeah, you just put the Pb2 plus. At Pb2 plus is X. So I just put X. And then the concentration of IO3 is 2X. Okay, double than this. Okay, so I just put 2X and then put to the power of 2. Okay, your what you need to do is to find out what is X. Yeah, so that is going to be the solubility. So I just need to calculate the solubility. So which is going to be 4x to the power of 3. When I cube root and divide by 4 and so on, I will get this value as my solubility. Okay, solubility is going to be mole per dm cube. So no need to convert anything. So you just need to write down the answer. Okay, done. Yeah. Next question. Yeah. So here, okay, this compound is an unstable compound, okay, that readily decompose, okay, when warmed. Okay, the decomposition reaction is shown. Okay, so you are going to use the data to calculate the entropy change of the reaction. Yeah, so in order to do this, quite simple. Okay, we just need to find out the entropy of the product, okay, minus the entropy of the reactant. So if you calculate, okay, this is make sure you put the half over there. Okay, all these values, and then these two you calculate accordingly. So once you put all these value, okay, this one is going to be the product. You minus the entropy of the reactant. Okay, you calculate all this, okay, and you will get positive 322. But do remember, this is going to be joule per Kelvin. So later, let's say they ask you to calculate Gibbs free energy and so on, you must be very careful. You need to change it into kilojoule later. Yeah, but in this case, this is going to be plus 322 joule per Kelvin. Yeah. Now this reaction is feasible at all temperatures. This one I already taught you. The moment, okay, if you have the entropy change is positive, delta H is going to be negative. The moment you see the two signs are different, okay, we can say whether the reaction is feasible or the reaction is non-feasible. If let's say it's going to be positive entropy, okay, and then negative enthalpy, so of course it's going to be feasible for all reactions. If it is the other way around, if it is going to be delta S is going to be negative, delta H is going to be positive, this one is non-feasible at all temperatures. Yeah. the one that we also learned, if it is the same, then it's going to be for certain temperature, then they are going to be feasible and so on. So that one I already taught you. Okay, but okay, now we need to use the data, okay, in F and answer this. Yeah. So here, okay, we know the Gibbs free energy. This is going to be, I taught you last time, Mr. Gopi is not so hot C. Yeah. So which is Mr. Gopi is not so hot. Okay, not so hot C. Yeah. So if you want to remember that, okay, please go ahead. Okay. So here, okay, is going to be, we know this is going to be always negative. Okay, always negative. Why? Because okay, it's given to us. Okay, it's negative. And okay, we know that this is going to be, they have mentioned, we have calculated is positive. Yeah. So if this is positive, we know that this value, okay, negative and positive. Yeah. So you see, it's always going to give you a negative value, or you can say the negative T, okay, at all temperatures, okay, at all temperatures will be always less than 0. Okay, it's always going to be less than 0. You can just write out like this. Okay, if it is always less than 0, and we know that delta H is also less than 0, okay, therefore Gibbs free energy is delta H, okay, minus this, okay, negative value, and the entire thing is negative. So it's going to be whatever, doesn't matter whatever temperature that we have, okay, your Gibbs free energy is always going to be less than 0. Okay, so that is how you explain. Okay, so if you look at the marking key also, you see Gibbs free energy is always negative. Okay, why? Because delta H is always going to be less than 0. Okay, and then the S is going to be always positive. Why? Because this is always less than 0. Okay, all the information that you need is all there, and make sure it's all temperature. Yeah, so you just write down accordingly. Okay, now number 4, this is very interesting question, okay, that I want you to focus. Yeah, the transition elements are able to form stable complexes, okay, with a wide range of molecules and ions. State the meaning of transition element. Yeah, what is transition element? It's an element that can form one or more stable ions with partially filled 3D orbitals. Everyone should know this. Yeah, so I'll just move on. Now, this is very important. Yeah, the d orbitals, okay, in an isolated transition metals are degenerate. Degenerate means they are going to be same energy level. But in complexes, the d orbitals can occupy 2 energy levels. This is what we call split into 2 non-degenerate orbitals. Okay, this is going to be, do remember, this is still, okay, the time that they are still using the old syllabus, but you see they have already asked question about that. So complete the diagram, okay, to show the arrangement of d orbital energy levels in octahedral and tetrahedral complexes. Now for octahedral, please remember I told you, if you have like this octahedral up and down, I told you up and down, if you have 2, yeah, you can memorize, okay, there are 2 orbitals at the top. Now you need to also remember, okay, this is degenerate orbitals, okay, there are 2 orbitals at the top, 3 orbitals at the bottom. But you also need to understand, you need to also memorize, okay, the orbitals are dx square minus y square and then dz square. Yeah, because they are asking question about this. Okay, that's why you need to know. Yeah, for tetrahedral, it's going to be the other way around. The 3 orbitals are the top, and the 2 orbitals that are going to be at the bottom, which is going to be lower energy level, they are also going to be dx square minus y square and then dz square. Yeah, that is going to be tetrahedral complexes. Yeah, so make sure you draw properly. But you see, this is very, very important because they ask you to sketch the shape of the 2 d orbitals. One, they want you to show the this one. They are asking for the octahedral complexes. Yeah, so the one lower energy. Yeah, the one lower energy over here. Okay, this is the common. Okay, which is going to be we have dxy. Okay, we have dyz. Okay, we have xz. Yeah, so this one is quite simple. Yeah, but if you don't know, then it's going to be difficult. Okay, so how to sketch? Okay, you see, I have drawn for you. Yeah, this is going to be x axis, y axis, at the top is z. So if you have, okay, they will just come like this. If you have y and x, if let's say like this and like this, they call it xy. Okay, dxy. So it must be in the middle. Yeah. So if you look over here, I have drawn. Okay, from here. Okay, let me erase first. Okay, maybe you can see better. Okay, I've drawn. Okay, so this is x. Okay, this is y. Okay, so I want to draw between x and y. Okay, so I draw one, and then here, and then okay, this is also x, this is y. So I draw here, and I draw here. Okay, this is what we call as dxy. Okay, the same thing if you have the other, okay, y, z, and so on, they will come in the middle. Yeah, so you just go and look at my notes. Yeah, now the higher energy level is very important, because the higher energy level you have, okay, two types. Okay, this one and this one. Okay, so if you want to draw, okay, you need to be very careful. Yeah, if let's draw the simple one, dz square. Yeah, dz square is going to be along the z axis. Yeah, so I'll just erase first, then we can draw. Okay, okay, this one is going to be dz square. You draw along the z, and then you put a donut in between. Okay, this is going to be dz square. And then, okay, there is another one which is going to be dx square minus y square. Now, this one, what does it mean? You draw along x, you draw along y. Okay, so let me erase this. Okay, it can be or, yeah. Okay, that's why. Okay, you can either draw this, okay, because you have two. Yeah, you can either draw this, or, okay, if I put like this and like this, z, x, y. So if I want x square along x, and then y square along y. This is going to be the answer. So you can actually use these two as your answer. Okay, they can ask you similar question like this, okay, for tetrahedral. Yeah, please remember this. Yeah. Now I'll move on. Now, EDDS, okay, and EDTA are polydentate ligands that form octahedral complexes with Fe3+. Yeah. So the formula is given. Yeah. So on the diagram, circle each atom that forms a bond with Fe3+. Yeah. So this one, if you want to circle, you're going to circle the the six, okay, they are going to be polydentate and they form six octahedral complexes. So they are going to be 6 coordination number. Yeah, so it means there must be 6. So we know, generally students will know that they need to circle the oxygen. Yeah, that one, no problem. Yeah. But okay, they also most of the students forget that nitrogen has lone pair of electrons, okay, which can actually give you the lone pair of electrons to form the dative bond. So this one is also going to be involved. Okay, the point that you need to take note over here is octahedral. So the polydentate, okay, is going to form 6 dative bond over there. Yeah, so that is going to be very important. 6. Yeah. Now. And then this one is very, very important. I told you why, okay, they are going to be 2 different colors, red and yellow. So you need to mention the DD orbital splitting, okay, will have 2 non-degenerate orbitals with different energy gap. Okay, so I put it in a simple form over here. You can explain more. Okay, because there are different energy gap because of the different ligand, okay, different frequency of light is absorbed and they are going to show a different complementary color. Yeah, so please include this. Yeah, please include, okay, different way. Don't simply say there is going to be DD orbital splitting and then you are going to get electron promoted or excited and then just simply like normal. Yeah. You say frequency of light is absorbed, complementary color is seen. You need to mention that there is going to be difference in energy gap because of different ligands. Yeah, different ligands will have different energy gap, and that is going to be the one that will give you a different complementary color. Yeah, please take note of that. Now, when this is added, okay, state the type of reaction. So you see this one, okay, this is going to replace this water ligand, so this is going to be ligand exchange. But before you write, always think, yeah, whether this is solid or not, yeah, or it's going to be acid-base reaction or not. Until let's say you notice, okay, this is going to be nothing to do with precipitation, nothing to do with acid base and some other reactions, then finally you give your answer as ligand exchange. Don't use ligand exchange as your main answer. Yeah, so this one, the best answer is ligand exchange. Yeah, so I'll move on now. Write the expression for the stability constant of this. So I have to took the equation that they have given earlier. So I brought it over here. So I need to write the stability constant. When you write the stability constant, okay, make sure, okay, you do not include the water. Yeah, water is going to be, they are going to be constant. Okay, similar. We don't include solid. Okay, so K step. Okay, when you write down the K step, okay, you just need to write down FE EDDS, okay, negative, okay, and then divided by EDDS 4 minus, okay, and then FE, okay, all of them 1 mole, so no need to worry so much. 3 plus, okay, close the bracket. Okay, this is going to be the stability constant. Okay, now the table below, the table shows the value of stability constant of both complexes. So let's say I put it as a K step 1 and K step 2 for later question. But if you look at K step, yeah, stability constant, the bigger value, you can see this is a bigger value. The bigger value of stability constant, that is telling us that that particular compound is more stable, that complex is more stable. So we can say that, okay, which one is more stable? We can say that FEEDTA is more stable. Okay, it's more stable. Explain your answer with reference to K step. You can say that the K step, okay, of this is more than K step. Okay, so that's why I think I use the 1 and 2. I can just simplify over here. K step 2 is more than K step 1. Yeah, so you explain properly. Yeah, so here, okay, when an excess of EDTA 4 minus is added, the following equilibrium is going to be established. Yeah, so they say this is the equilibrium. Yeah. Now, what we need to do is, okay, we need to calculate the Kc. Okay. Now, Kc, okay, for this equation, okay, I have written down for you. Okay, these are all aqueous. You can see clearly. Okay, so I have written EDTS. Okay, this one. Okay, you can just check. Yes, all that. So once I have Kc, okay, what they are asking me to do is, okay, they're asking to use the data that I have. Like, for example, the first K step, okay, you see the one that is involving K step 1, okay, K step 1 involving EDDS, yeah. So if I just use the K step, this is the value, yeah. So I took the same value, yeah, the same value. You can see the same value. I just put it over here. This is the same value. Okay, I'll make it bigger. Okay, you can see. And then, okay, I need to write for this equation for the EDTA. Yeah, so K step 2, I need to write. Okay, how do we get that? Okay, we get, okay, of course, similar with water. Okay, and then you add with EDTA, they are going to give you this, and then 6 water molecules is going to go out. Okay, so of course, this is liquid, similar like just now for the EDDS. Okay, when you write the K step, you get this. Yeah. Now, I remember just now I put it as K step 1 and K step 2. Okay, K step 1, I put K step 1, K step 2. Now, I'm going to use these 2 equations, okay, 2 equations to get this or to derive that. And when I see that, okay, I see the EDDS 4 minus is on the top. Okay, and you see EDDS 4 minus is at the bottom. Okay, what I do, trial and error, yeah, I can change the position. Okay, when I change that position, that is going to be 1 K step 1. Okay, so that is going to be, I try to change the position. If I change that position, what will happen? Yeah, I know that, okay, I will have the EDDS 4 minus, okay, then FeH2O6 3 plus at the top, and then FeEDDS minus over here. Now, here, okay, I still want to maintain FE over here because it's the same here. So what I do, okay, I just select this. Okay, I try to times, okay, with these two. Okay, when I times these two, okay, you will see something. Okay, this one, when I times this, okay, this value will cancel with this. Okay, and what I notice, okay, I have EDDS for minus, I have this, and I have this. Okay, it means that in order to get KC, okay, this is the one that I flip. So this is going to be 1K step 1. Okay, times K step 2. I will get KC. So I just need to use the data that I have over here. Okay, this data. I just need to put them in. Okay, put them in. 1 over K step 1, okay, 3.98. Yeah, so you see 3.98. And then times K step 2. Okay, just times with K step 2. Okay, and I will get, okay, this value. So you just need to confirm only. Okay, no need to show everything. Yes, the moment you get the KC, if you can get the relationship, yeah, then it's okay already. 3.17 times 10 to the power of 4. I do this just to confirm. Yeah, just to confirm. Okay, so it is very important. Trial and error. Yeah. Now, number 5. Okay, carboplatin and satraplatin are used as anti-cancer drugs instead of cisplatin. Now, this one, don't need to worry. Describe the action of cisplatin as anti-cancer drug and so on. Okay, now no longer in your syllabus, but to remember, even though they remove, yeah, just learn a bit here, okay, how cisplatin can react as anti-cancer drug. Okay, cancer is going to be something that can replicate a lot. So what the cisplatin will do, they bind with the DNA and then prevents replication of cell division. Yeah, that's 2 marks. Okay, if you don't want to know, so it's okay, fine. Yeah, no longer in your syllabus. Now, suggest the geometry of platinum center in carboplatin complex. You see carboplatin complex, the coordination number is going to be 1, 2, 3, 4. If it is 4, this is going to be, in this case, they are going to show, they are showing it in this form, yeah? You see 2 going behind, 2 coming in front. So they didn't show it in this form, okay? If they show it in this form, then it's going to be different. This is going to be tetrahedral. This is going to be what we call a square planar. Okay, so square planar. Now, suggest why carboplatin does not show cis and trans isomerism. So if you look over here, if you want to show cis and trans isomerism, this ammonia and this ammonia is side by side. This is cis, yeah. But if you want to have trans, then the ammonia must come over here, opposite over here. The problem is not the ammonia. The problem is this particular molecule, okay? This O, then this one supposed to come over here, yeah? And what is the problem with that? It's going to be, it is quite difficult, okay, to bring this O to come over here. One is the distance, okay? The distance, the ligand cannot cover that distance. Second, they are not able to form that bond angle. Yeah, they cannot form the 180. They can only form the bond angle, which is going to be 90 degrees. Yeah, you can see from here to here is 90. So they don't form, okay, because that is going to be, they have to cover the 180. So if you try to understand what I'm trying to say, maybe something like this. They have means they cannot form, okay, like this, okay. How, yeah, like this, something like this, yeah. So they cannot form the 180. Yeah, it's not possible. Okay, the reason, okay, I already mentioned to you just now. Yeah, so here, okay, the bidentate is a bidentate ligand. They are not capable to form trans isomerism. Okay, cis, no problem. Okay, trans cannot because the distance, the long distance, and then it's not capable to form the 180-degree angle. Yeah, so it's the bidentate will have that problem. Okay, there are certain ligands that are possible to do that. Okay, like for example EDTA, yeah, polydentate, they can form the entire octahedral structure and so on. So in this case, this ligand is not capable. That, yeah. Now, Satraplatin is a neutral complex, containing all these ligands, deduce the oxidation state. Now, in order to do this, don't just simply look over here only. Oh, there is going to be 4 ligands. Then you will make a mistake. They say satraplatin. Satraplatin is this one. So you know that they have already mentioned just now. This is going to be neutral. They say the entire molecule is neutral. And we know the oxidation state for ammonia is going to be 0. And then this is also neutral. And then the Cl and Cl is going to be -1, -1. So let's check again. This one also -1 and -1. So if you're not sure, you check again. Cl -1. This is going to be -1. So you see here in this molecule, I have 6 molecules or 6 ligands. And you see platinum, when they join, you see -1, -1. So -2, and then 0 and 0. So 2 times 0. And then, -1 and -1. So this is going to be -2. What is the overall charge of this satraplatin? So 0. So I can find out what is the charge for oxidation number for platinum. So platinum is going to be -4. Equals to 0. Platinum is going to be +4. So if you don't, if you miss out, you just take like this alone, you might actually get +2. It's not +2, it's +4. Refer to the diagram. Very, very important. Don't make that kind of mistake. Even though it's 1 mark, don't make that mistake. Now, if we move on, the compound M is made of 1,3-dimethylbenzene in 2-step synthesis. So if you look at this compound, if you write down, there are 2 parts. So I just put C6H4, and then you have CH3. You'll get this. If I join them together, I know that this is going to be C8H10, and this C8H10, you are going to get C8H6O4. So this is going to help me. Once I know this, it's going to help me that I am going to have suddenly 4 atoms of oxygen. And in that process, my hydrogen is decreasing. So I can just tell, most probably this is oxidation reaction where my methylbenzene, the methyl over here, change into carboxylic acid. That's the only way where you can get the 2 oxygen over there to get 4, and then the hydrogen can go missing, because the CH3, all the hydrogen is going to be missing a bit, so I can get. But just to confirm, I just count. I just count. When I count, I will get the C6, H4, and then COOH2. When I count C8, 2 carbon over here. So H is going to be 2 here, 6, and then O2, sorry, O4, 2 and 2, O4. And you see it matches, The moment it matches, we know this is going to be oxidation, And then, after that, there is going to be step number 2, which is going to be the carboxylic acids over here. They are changed into Cl. So this one quite simple. How to change carboxylic acid and to change it into acyl chloride. So you just react with PCl5. You can react with PCl3, but you need to heat them. So if you have SOCl2, this is going to be room temperature, but this is not popularly used because they are going to give you SO2 and ACl. ACl is okay, SO2 is acidic, and ACl is also acidic. They say it's poisonous, SO2, more poisonous, So it's going to be still okay, PCl3 or PCl5, So up to you, which one, But the popular one, they always, in the marking key, they put PCl3 and PCl5, Now, here they ask you to draw the structure L, I already know it's going to be carboxylic acid over there, but I need to, since they give you in the skeletal formula form, they didn't specify, so I try to draw them in skeletal formula. You try also do the same thing, don't show the carbon, so I don't show the carbon, I just put something like this, so this is going to be, but make sure, you are focusing at these 2 positions. Don't go and create new position as you wish. It's not possible. So once you do that, that's going to be structure L. Suggest regions and conditions for each step of this synthesis. So the region is going to be for oxidation. You need to be careful. Okay, it's going to be slightly different than the common oxidation because they are going to use alkaline KMnO4. Yeah, then only they acidify, and then you need to provide heat. Okay, so in normal condition oxidation, we just use acidified KMnO4. Yeah, but this one, okay, for metabenzene, we need to use alkaline KMnO4 and then acidify. And then the last one, okay, the step number 2 is going to be you need to use PCl5. I selected PCl5, and the condition is going to be room temperature. Yeah, and then writing the equation for step number 2. What is step number 2? So you see C8H6O4. Yeah, and then you are reacting with PCl5. Okay, basically what happens, okay, is going to be if you have, okay, RCOOH, okay, when I react with PCl5, okay, what do I normally have? It's going to be RCOOCl, okay, and then you have POCl3 and HCl. No need to balance, something like this. Okay, but now, okay, you are going to have another COOH here. Okay, so what you need to do, okay, then they are going to have, okay, another COOCl here, of course. Okay, and then because there's another 2 COOH, then of course this one must use 2, and this one also, okay, must be 2, and this one also must be 2, double. Yeah, double. So you just need to put the double over there. Okay, same. Okay, you can just count from here. It's okay. Then 2 POCl3, 2 HCl. Yeah, so easiest way you can start from here. Yeah. Now, a student investigates a possible synthesis of M directly from benzene using COCl2 with the presence of AlCl3 catalyst. If you have AlCl3, it means you are going to try to do direct substitution. Yeah, so this is going to be, they're talking about acylation. Okay, Friedel-Crafts acylation. Okay, so they are trying to use the halogen carrier. So benzene initially reacts with the COCl2 as shown. Yeah, so you have this, okay, and then they give you this. Okay, this one you are creating electrophile. Okay, because we know this benzene, they always react in form of electrophilic substitution. Yeah, so they will react. So this one is going to be the electrophile, and they are going to give you this. So suggest a mechanism. Yeah, it's electrophilic substitution. So when I draw, okay, you see this is going to be the electrophile. When you draw, okay, make sure you show the movement of the electron from the benzene ring to the carbon, which is the positive. Okay, so don't go the other way around. Very important. Once you have that, they will form the bond, and you are going to have something like this, and then you put the positive there, and then include the hydrogen so that easier for us to show the line, the electron going in. Okay, you have this, so this one will go in. Okay, the arrow. Okay, to make this complete. Okay, replace the 2 electron that is lost over there. So you are going to have the substituted chloride like what they want, and then you have H plus. So this is the mechanism. Done. 3 marks. Okay. Now, this is a very interesting question. Yeah, so fumaric acid is naturally occurring dicarboxylic acid. Yeah, so they ask you, yeah, find out the product between, okay, fumaric acid and excess hot concentrated. Now, if it is hot concentrated acidified manganate, yeah, this is going to be whenever you have C double bond C, yeah, they will undergo oxidation. Okay, we learned this under alkene. Yeah, so what happens? Okay, they will undergo oxidation. Yeah, and depending on what you have, yeah. So in this case, you see, when I break, okay, I will get, okay, you see this carbon has hydrogen. I'll just rewrite again, C, okay, double bond. This one always will become O, okay, you have H, and this is going to be COOH. Okay, I'll put over there. Now this one, okay, whenever you have hydrogen over here, okay, and then 1 R group, okay, this is going to automatically change, okay, into carboxylic acid. Yeah, how to say it's carboxylic acid? You can see, you can hide this this part, C double bond O. Okay, then automatically this one. Okay, this actually looks like aldehyde. Yeah, aldehyde can be further oxidized to give you carboxylic acid. So this is going to be what is going to be formed. So if you look at this side, okay, same, you are going to get O, you put O over there, okay, and then the carbon, and then you have, okay, one hydrogen, okay, and then CO2H. This is like, looks like R, and then this is going to be aldehyde. So aldehyde can be further oxidized, so you get carboxylic acid over there. Yeah, so both of them are the same. Yeah, you can see over here they are the same. Now, one thing that you need to take note, yeah, they are going to produce one product. Yeah, which is, I'm just going to look at it like this. Yeah, they are the same. But when I rewrite them again, okay, you see C double bond O, OH. And then there is another C double bond O, OH. What is this? Okay, this is ethane dioic acid. Now, ethane dioic acid in our syllabus in A2, maybe your AS, you don't know, but in A2, okay, can be carboxylic acid be oxidized. Yeah, carboxylic acid generally in A2, we know that they don't get further oxidized. But in A2, I told you that, okay, methanoic acid and, okay, ethane dioic acid can be oxidized. For ethane dioic acid, you need strong oxidizing agent, which is this. Yeah, but methanoic acid, even like you use a strong oxidizing agent, failing tolerant, all, okay, they can be oxidized. But in this case, if you want to oxidize this can be further oxidized to give you what? Okay, they are going to give you carbon dioxide and water. Yeah, so these are the two products that you are going to get. So, okay, don't go and write down ethane dioic acid. You will not get marked. Okay, identify the products. Yeah, so it's carbon dioxide and water. Okay, now fumaric acid can form addition and condensation polymers. Draw the repeat unit of addition polymer. Yeah, so addition polymer. Okay, so let's actually draw the addition polymer. Okay, so I'll just use carbon, okay, double bond carbon, okay, then I will just write down hydrogen. I bring the COOH here, and then I put COOH over here, and then one hydrogen over there. So repeat unit, yeah, so the double bond is going to be broken, yeah, so you just need to put like this, and like this. So this is the repeating unit, yeah, draw the repeat unit, yeah, this is the repeating unit, okay, so the answer also you can see, okay, let me check. Yeah, so this is the repeating unit. Okay, now, if more than one unit, allow one unit identified. Yeah, so don't draw more than one unit. Yeah, now draw the repeat unit of the polyester form. Yep, they already say it's polyester. Okay, ethane 1,2-diol. Yeah, so what is ethane 1,2-diol? They even help you over here. So ethane, so carbon 1,2-diol. Yeah, why 1,2-diol? Okay, because you see, if you use the diol, yeah, later part there's a question. Yeah, diol can be formed if you use excess hot concentrated. You get the if you use excess concentrated, then you get the something like this. Yeah, if you have the double bond is broken, then you have the oxidation. But if you have carbon double bond like this, okay, if you use dilute, yeah, and then cold condition, yeah, you are going to get diol. The OH will come here, the OH will come over here. Later we'll see. Yeah, there is a question over there. Now here, okay, if I put over here CH2, yeah, so CH2 OH2, so this should be okay. Now, just to make our life easier, I'll bring the OH over here, left and right. Okay, OH, hydrogen, and then I'm going to react with fumaric acid. Yeah, fumaric acid. So I'll draw just to make our life easier also. Okay, you see carbon, double bond carbon. Okay, and then I can see the hydrogen there. Okay, and then I put carbon double bond OH here. Okay, and then I put carbon double. Okay, there is hydrogen first. Okay, hydrogen. Okay, then carbon double bond OH. So now we want to find the polyester, and then we need to show the ester bond. Yeah. So here, okay, what will happen? Okay, the OH from here, H from here. Don't make that mistake, yeah? So H from here, okay, OH from here, okay? So when you draw, you just draw like this, O, CH2, CH2, O, join with C, double bond O, CH, double bond is still there, CH, C double bond O, join like this, yeah? And then you need to also show, okay, the ester bond, okay? So I use this pen and I show like this, okay? This is the ester linkage or ester bond. Done. Okay, draw only one unit here, don't draw more. Okay, in this case, they are using skeletal formula, but they didn't ask to use the skeletal formula, so it's okay. Okay, I'm fine. Okay, now explain why polyester normally biodegrade more readily than polyalkanes. Yeah, polyalkanes, you can see all of them are saturated bond. Yeah, saturated bond, they are not going to react. Yeah, so they are not going to be undergoing hydrolysis. Yeah, polyester. Okay, polyester contains ester bond. Okay, ester bond which can be hydrolyzed. Okay, hydrolyzed easily under acidic or alkaline condition. Okay, and then polyalkanes. Okay, polyalkanes only has saturated bonds that is difficult to be broken or cannot be hydrolyzed. So they actually mentioned non-polar cannot be hydrolyzed. Okay, polyester can be can undergo hydrolysis. Okay, so I think the best answer is the polyester can undergo hydrolysis. Done. Yeah. Now fumaric acid reacts with coal. This is what I told you. Under cold condition and acidified dilute, okay, you are going to get, okay, the OH, the diol, okay, the C double bond will break. Okay, the double bond will break, and then you will get the OH and OH over there. Now, they say that only 3 stereoisomer exist. So they say that they draw one of the stereoisomer over here. So this one, you can see that, okay, they are going to have something like a chiral center. There are 2 chiral center here, 1, 2 here. Okay, and if you try to draw, okay, the stereoisomer over here, some sort of if you look at it, okay, you can see that COOH here, COOH over here. So what I do, yeah, I put the COO. They have given us like this, and so I put the COOH over here, and then, okay, I know that, okay, this is, if I put, then it's same like that. So here, what I change, I put the OH, I bring it over here. I change position, yeah. And I put the OH over here, I put over here. Okay, so you see, I put the OH here, H over there, change position. And then the H and OH, I change the position. Yeah, so that's the first one I did. Now, second thing that I did is, I cannot actually change, how, yeah? In this case, the second one, okay, what I did was, okay, I still maintain the COOH over here. Okay, I still maintain. Okay, but, okay, rather than just switching, yeah, you see H and H is here. What I did was, okay, I put the OH here straight. Okay, I put the, in this case just now, I put it straight OH, OH over there. Okay, so what I did over here, okay, I don't want the OH and OH to be together like this. So what I did, I put H over here, OH over here, and then H over here, OH over here. They are going to be different. Yeah. So that is how I play around. Yeah. And you can see that, okay, these 2, they are going to be different, and this is different. So you have 3. Okay. There are going to be other ways that you can play around also. Yeah. Where, okay, the one that we did is OH and OH is over here. we also put the H and OH like my answer just now, or you can also put the OH over here. OH is over here, and you put the H over here. Okay, H over here. Okay, so in all this, okay, we are maintaining the position of, okay, CO2 H. If you change, then everything is going to be different and it's very difficult to look at. Yeah, so this is going to be the stereoisomers. Yeah, that. Now this one, okay, I will skip, okay, because it's no longer in our syllabus. So let's actually skip this enzyme. Yeah, no need to worry about that. Okay, let's move on. Okay, question number 7. Okay, so for question number 7, okay, proline is a naturally occurring amino acid. Yeah, so proline is often found bonded to glycine in protein. Glycine is going to be, you see, the important thing over here, they say naturally occurring amino acid. We learned that, okay, amino acid must have hydrogen, yeah, must have NH2, okay, must have COOH, must have R group. Okay, but if you look at here in this example, it's unique a bit. Yeah, there is COOH, okay, but here there is something like NH, yeah, so it's not NH2, okay, so this is also classified, yeah, as going to be amino acid, okay. Now, if you have glycine, yeah, glycine is going to be the R group is H, yeah, so this is going to be glycine. So they want you to draw a dipeptide, okay, proline and glycine, and the peptide bond must be shown clearly. So what happens, okay, is going to be you are going to react, okay, the these two, okay. So let me erase this, okay, and then I select the same thing, okay. I'll bring it over here, okay. I put over here, and then now I'm going to react, okay, with NH2. So this one I'll write, yeah, NH, and then CH, COOH over here. Okay, what happens? Okay, the hydrogen from here and then the OH over here. Okay, they are going to react. Yeah? So that is going to be the only thing that is going to happen. Yeah, and then okay, the another thing that is going to happen over there. Okay, is going to be. Okay, you can see here they have shown in skeletal formula. Yeah. So what they are going to give you H2O. Okay. So you just need to rewrite this again. So I'll just rewrite. Okay. They want us to draw. Okay. So actually not the equation. So let me just select this, make it smaller. Here, make it smaller. Okay. So if I draw, so it's going to be like this, N, H, then this is going to be double bond O. This is going to be bonded to nitrogen, and then there is hydrogen. So I'll show the hydrogen here. Then you have carbon, hydrogen, and then C double bond OOH. If you want to change them into the skeletal formula, yeah, so you can just put the NH over there, is okay. Then the carbon, they have 2 carbon. Okay, so I'll just put 1 carbon, 2 carbon, and the last carbon has carboxylic acid group. So you can just leave it like this. Okay, so this is going to be the equation. Okay, for the not equation, the structure of the dipeptide. And then they say the peptide bond must be shown. So I'll just show the peptide bond. Okay, this is the peptide bond. Okay, name the type of reaction that forms a dipeptide, okay, from 2 amino acids. Okay, this is going to be condensation reaction. Yeah, so condensation reaction. Next, okay, proline is able to form polyproline peptide chain. Okay, then they ask you, yeah, this one secondary structure we didn't not in our syllabus, but they say why it cannot be stabilized by hydrogen bonding. Now, stabilized means, okay, the bond, yeah, must be between here must be some kind of a hydrogen bond should be appearing, and then it will stabilize the structure. But in this case, they are asking why it is not stabilized by hydrogen bonding. Because simple, okay, because each nitrogen can have only 3 bonds, so there is no hydrogen. So hydrogen, in order to have hydrogen bonding, yeah, hydrogen is bonded to hydrogen, nitrogen, oxygen, and F. I have oxygen, I have nitrogen, but there is no hydrogen. Yeah, so if there is no hydrogen, so definitely you are not going to have hydrogen bonding. So the reason is because no hydrogen attached to N. Yeah, so that's the reason why it cannot be stabilized by hydrogen bonding. Anyway, they are not going to be asked. Okay, this one may be just additional knowledge. Okay, now the next question is going to be the reaction scheme shows several reactions of proline. So you have this amino acid. Okay, amino acid, you have reaction with sodium hydroxide. Now you see amino acid reacting with sodium hydroxide, it must be the carboxylic acid is reacting with the sodium hydroxide. So I have written, yeah, so this one O minus Na, the salt and water. Yeah, so the reaction 3, okay, you can see the reaction 3, I have carboxylic acid suddenly changing into alcohol. Okay, carboxylic acid changing into alcohol, okay, only one way. And you can see it's going to be primary alcohol. This is going to be reduction. Yeah, carboxylic acid reduced to become primary alcohol. You can use, okay, the reducing agent. Yeah, so I have put over that. And then if you look at reaction 2, okay, I noticed that, okay, you have C7H11NO3, and then I have CH3COCl. Okay, so how, okay, this reaction is going to happen? Yeah, so if I look at it, okay, if you look at the number of carbon, okay, let's look at the number of carbon, 1, 2, 3, 4 carbon, and then you are adding 3, hold on, okay, 1, 2, 3, 4, 5 carbon, okay, and you are adding another 2 carbon over there. Okay, so what is happening over here? Okay, they are going to actually react. Okay, this one, okay, carboxylic acid, okay, carboxylic acid, and this, okay, amine, and then they react with this. Yeah, maybe later we need more information on this. Yeah, so let's actually hold on to this first. Okay, now write an equation, okay, for the reaction of proline with NaOH. Yeah, so just rewrite this again. Yeah, so plus NaOH. Okay, and then this one, how to write? Yeah, so C4H7, okay, and HCO2 minus Na plus. Okay, you just rewrite. Okay, so you just know lah. So 1, 2, 3, 4. Okay, C4. Okay, then I think this one also I think is already given. Yeah, so it's already given. You can use this. Yeah, C4H7 and HCO2 plus minus. Then you just put the Na plus and then water. Okay, done. Yeah. So sorry, it's not water. Yeah, it's hydrogen gas. Okay, my bad. Yes, it's going to be sodium hydroxide. Okay, it's going to be O and A. Okay, hold on. Okay, carboxylic acid, okay, plus sodium hydroxide. Okay, acid and base is going to be water. Okay, so it's correct. Okay, plus water. Okay, unless they are reacting with sodium, then it's going to be hydrogen. Yeah, so this one is correct. So proline, okay, is it has, okay, a secondary amine functional group. Okay, so they have secondary functional group. Okay, secondary amines, they already mentioned they react with acyl chloride. So they already mentioned, I think this is going to help this. Yeah, secondary amines react with acyl chlorides. For example, dimethylamine reacts with ROCl. Okay, with the following equation. So if you have something like this reacting with this, what will happen? Okay, they already say this hydrogen will go out with the Cl, and this RCO will come over here. Yeah. So suggest the skeletal structure for R. Yeah. So here, when you have this similar reaction, okay, when you suggest, okay, you just draw like this, and so this one, nothing will happen this side. So double bond OH. So this H will be gone, okay, will be gone, okay, will be replaced with the Cl over there, ACl. So the part that is going to be left is COCH3, okay. So this one is going to be COCH3, supposed to be like this, okay. So this one I want to also show a skeletal structure, yeah. So I cannot simply draw like this. So I have 2 carbon, okay. So maybe I draw 1 carbon, 2 carbon, okay. And this carbon has, okay, O over there, okay. So this is going to be the answer, okay. No need to show the hydrogen. So this will be the answer. Okay, they say product skeletal structure of R, so no need to write the ACl also. Okay. Now suggest the region required for reaction number 3. Okay, so I already told you it's going to be a reduction. Yeah, so you need to use LiAlH4 in dry ether. Okay. Next, okay, proline was first synthesized in lab, okay, using a multi-stage synthetic route. Okay, so they say stage number 1. Yeah, so they ask you to name all the functional group present in reactant in stage number 1. Okay, so you can see, okay, when I rewrite this also, okay, I have this structure, yeah, and I can see that they are ester bond. Okay, they are ester. This is also ester. Okay, so the functional group is ester. Yeah, nothing else. Yeah, and if you want to be specific, also, if you want to say there are 2 ester inside, so you can say diester also can. Yeah, if you write ester also okay. Yeah, and then okay, for this compound, yeah, you can see here I have 2 functional group. One is double bond, another one is CN. Yeah, so the double bond, okay, you can say alkene. Okay, the CN is nitrile. Yeah, so you must mention these 2. Yeah, suggest the type of reaction that occurs in stage number 1. You can see the stage number 1, what happens, okay, this compound, okay, the double bond is broken, then something comes over here, and then something comes over here, yeah, which is that something, yeah, is going to be this, okay, and then this, yeah. So what is actually happening over here? Suggest the type, okay, is addition reaction, or you want to write down electrophilic addition also can. Yeah, suggest only. Yeah, no need to be so detailed or crack our head about it. Yeah, it's addition reaction because double bond is broken. Yeah, now the next part is going to be, okay, you react with region V to form W. Okay, so when W is formed, okay, so we can see, okay, what happens over here. Okay, the moment I can see everything is the same, except the CN is changing into NH2. Yeah, so what happens over here? This is going to be a reduction. Yeah, so suggest a suitable region V. This is going to be reduction of nitrile. Now, reduction of nitrile last time, okay, they used to have 3 conditions, okay, but in your current syllabus they have removed one of the condition. Okay, you can use LiAlH4 in dry ether. Okay, you can also use, okay, hydrogen in nickel catalyst or hydrogen with platinum catalyst. Okay, you can do that. Okay, hydrogen in palladium also can. Yeah. Then last time they say sodium in ethanol. Yeah, but sodium in ethanol, okay, they have been removed from the syllabus. Okay, so therefore please avoid using this. Okay, I will suggest to remember this one. Yeah, so I'll just use LiAlH4 in dry ether, or if you want platinum with H2, is up to you. Yeah. Now, stage 3 takes place in the presence of acid catalyst. Yeah. So this is the stage number 3, acid catalyst. Let's see what is happening. Okay. When I see here, suddenly something is reacting and suddenly you have a cyclic structure. So when I see something like a cyclic structure, this one, okay, remains unchanged. Okay. So I know that something happened. Yeah, something happened. Okay, between, okay, okay, something happened where, okay, the reaction, okay, they say acid catalyst, okay. So what happened, okay, you can see, if I look over here, okay, if it is acid catalyst, okay, so it's like this, okay. If you have acid catalyst, the first thing that is happening over here, okay, is going to be, if you just simply look over here, then it's going to be C double bond O, then C2H5 is ester, this one ester, okay, and then this one also ester, okay, but this one is not reacting, okay. But when I see over here NH2, they are kind of reacting with this molecule, okay, but ester don't react with don't simply react with the NH2 just like that, yeah. So what you need to do is to break, yeah, you need to break the ester bond first, yeah, and acid catalyst can help to break that bond, hydrolysis, yeah. So when you break the bond, what happens, okay, because here only one O, yeah, so there is another O is gone, yeah, so it is gone to become the product Y, yeah. So what happens here when this is broken, so you have C2H5OH, okay, that is going to be product Y. And once that is broken, yeah, you are going to get, okay, carboxylic acid. Okay, this one become carboxylic acid, and this part. So carboxylic acid, we can react with amide, yeah. So what happens, okay, this hydrogen from here and the OH over here will join, and then they will join with that, and they will form the cyclic compound, okay. So what happens, one of the hydrogen over here came out, okay, and then the OH over here will come out, so they are going to give you water, and they will join with the carbon and oxygen, okay, carbon and oxygen, and this is a cyclic compound, done, yeah. So suggest the type of reaction that occurs in stage number 3, okay. Stage number 3, okay, if I want to suggest, I'll say the number 1 must be acid hydrolysis. They didn't include in the marking key acid hydrolysis, but I will also include, yeah, after that, okay, because there is going to be water is going to be eliminated over here, okay. It's just going to be elimination reaction or condensation reaction. So this is going to be more forming the amide linkage, yeah, amide linkage. So the answer given is elimination and condensation, okay, but I still also feel that acid hydrolysis should be also there, yeah. But condensation, don't ignore that as well, yeah. So condensation and acid hydrolysis. Deduce the identity of Y, yeah. So Y is going to be ethanol. Next, okay, after several further stages, Z is produced, okay. In the final stage of synthesis, Z reacts via a nucleophilic substitution mechanism. So this one, last time we learned under halogenol alkane, okay, to form proline. So complete the diagram to describe the reaction mechanism, yeah. So this one, okay, nucleophilic substitution, if you forget about this, yeah, you see this one, okay, is more electronegative, so delta negative, and this is delta positive. What will happen next, okay, we do have, okay, nitrogen having lone pair of electron, yeah. You can actually show the arrow here, or you can even show in the intermediate also, okay. So here I think better to show it over here, because here they want you to draw the intermediate, yeah. So you just put over there, okay. So the intermediate, okay, the moment they come over there, okay, you are going to get, okay, I think if I put the delta plus, okay, plus over there, if I put this one coming over there, okay, that is already going to join, okay, to give you this structure proline, okay. But when they go here, okay, so you are going to get, okay, this structure, okay, draw the structure of any intermediate ion, okay. This is Cl, but this is Cl is non-organic, yeah, but if you want to keep it over there, you keep it, yeah, so you will get the positive over there. So this one will go there, okay. Once it goes there, then you can see nitrogen, okay, and then they form bond over here, so there's going to be 1, 2, 3, 4, Okay, so 1, 1, 2, 3, 4. Yeah, so it's correct. So then you get this. Okay, so this is going to be nucleophilic substitution. Okay, so the mechanism you can see. Okay, it is important to show this. It is important to show this. Important to show delta plus. Important to show the lone pair of the electron. Okay, and then it is important to show this as well. Yeah, now identify, okay, the chiral center. Okay, you see this one, each of them have 2 hydrogen. Okay, you want chiral center, it must be 4 different groups, and you can see this is going to be the one that I identified, because yeah, one group, another group, another group, one more is hydrogen. Yeah, skeletal formula no need to show. Yeah, so the asterisk you just draw over here. Okay, now the next question is, okay, part of the structure of gelatin is shown. Yeah, so you need to find the number of amino acid. Yeah, so if you want to find the amino acid, you need to hydrolyze them. So you need to identify the amide linkage. Yeah, so identify, break. Okay, identify, break, identify and break. Okay, CO, identify. This one nothing to break. Yeah, so here identify and break. Identify, okay, here also, okay, and then finally here. Now the one that confirm we know is amino acid, because this one is OH, this one NH2, you see H and R, okay, 1, okay, so it's the same also, 1, 2, okay, this is also amino acid, no problem, okay, amino acid, okay, COOH, NH2, 1R group, 1H. Okay, the one that is in blue, no problem. Okay, but do remember, just now I told you to take note of the this structure, proline. They say proline is also amino acid, and then you look at the way proline is written. COOH and then NH can be there. No need to be exactly NH2. So, okay, if you look at the diagram over here, okay, you see here, the NH will come over here, similar to proline. Yeah. So yeah, that is going to be included. Okay. So this one is going to be included. Okay. Also. Okay. And then you can see that this is also included, and H. And this is also included, and H. So when I count, okay, 5, okay, 6, okay, 7, okay, 8, and 9. Yeah, there are total 9 amino acids over there. Yeah. Now at pH 6.5, proline exists in aqueous solution as zither ion. Okay, you need to draw the structure of zither ion. This is the structure of proline. Just now I took it from the question. So the H will come over here. Yeah, they will come over here. So you will have, okay, this, okay, and then the NH2. Okay, then you will have the plus over there. So if you want to show in terms of skeletal formula, okay, how you can show, maybe you draw like this, and maybe you write down H2, you put like this, okay, then this one, okay, and then double bond O minus, okay, and then don't forget plus. Okay, must draw the plus. Okay, so explain how. Okay, the H plus comes from COOH, and then the H plus goes to nitrogen. Okay, so you explain about that. Now the isoelectric point, okay, is going to be the pH where it exists, okay, as zither ion. Okay, 3 of the amino acid are proline, alanine, glutamic acid. Their isoelectric points are shown. Yeah, so we know, okay, under these isoelectric points, okay, so they are going to exist in form of zither ion. So they are in form of zither ion. Okay, now if it is going to be at zither ion, so what will happen? Okay, we know that they are going to have COO minus, and NH3 plus. Okay, this is COO minus, NH3 plus, COO minus, NH 2, and then still plus. Okay. Now, if you look at it, plus and minus, then they are neutral. Okay, don't have overall charge. Plus and minus, they are neutral. Okay, if they are neutral, okay, if you just use the pH just normal, they don't move anywhere. Yeah, but yeah, so in this case, you see here -2, okay, and then plus. Okay, so in the end, they are going to be overall -1 charge. Yeah. So now, okay, glutamic acid, okay, you can be sure that they are going to go to the positive terminal. Yeah, so I put positive terminal. Okay, but do remember that they are using pH 4 also as a buffer. Yeah, so if pH 4, okay, do remember they are not going to stay in the middle. Okay, these two. So pH 4 is going to give you the H plus. Okay, what happened to the H plus? Okay, the H plus will come here and then make this as COOH. The H plus will come here, make this as COOH. Now it's no longer neutral. Okay, now they are going to be positively charged. They are going to be positively charged, but still the charge is +1. Okay, still +1. Okay, so what is going to differentiate them? Both of them are going to go to the negative terminal, so they will go over here. But which one is which? Yeah, so you can see the structure. Yeah, there is more carbon here. Okay, and then less carbon here. We know this Mr is more. Okay, the Mr, which is going to be more, yeah, they are going to travel less. Yeah, they're going to be separated less. So you can see this one, okay, should be proline. And this is going to be alanine, yeah, because they are going to be Mr. Yeah, we talk about Mr. So there is going to be a few things that you need to mention about. Okay, what happens over here? Explain your answer. Okay, why glutamic is going to go to the positive? Why this one is going to go here, and why there is separation because of the Mr. So all this, okay, you can refer to the marking key over here. You see, glutamic acid will go to the positive end. Okay. Then proline, alanine, they will go to the negative end. Yeah, this one is already done. Yeah, you will get 2 marks for that. But you need to mention, okay, why they go to the positive? Because they are negatively charged. I already told you they are negatively charged. And then, okay, they go to the negative because it's positively charged. Because why? It contains this. Yeah. So they are going to have, okay, the NH3 plus or NH2 plus. Okay, it's positively charged. And then you also alanine, why it moves further. Okay, you need to tell the Mr is smaller, lower Mr. Okay, so you need to explain all that, and all that will give you a total of 4 marks. Okay, now the next question over here. Yeah, this is a very interesting question. Okay, I put the question over here again so we can go through this. Okay, so you see here, okay, the anion, okay, of the sodium salt, okay, they are a strong base. Yeah, so this is not an ion. Yeah, so aces is going to be a molecule. Okay, and then when you have this salt, then it's a very strong base. Yeah, a buffer solution, okay, is going to be prepared, okay, using the following steps. Okay, so if you have, okay, you have this with Na, so they say you take this entire thing. Okay, it's not aces now. Okay, it's going to be anion of the sodium salt. Yeah, so this with Na plus, yeah, and O minus. Yeah, so here, okay, this one I just need to change into O minus and Na. Yeah, just follow this one. Now, this one when you dissolve, okay, at 100 cm cube, okay, with distilled water, and you use 3.5 gram. Okay, you put over there, and then, okay, you are going to add, okay, a certain amount of hydrochloric acid over there, okay, because they say it's a strong base. Yeah, so I can calculate the number of moles of HCl, okay, which is you count, okay, 50, okay, times 0.2 divided by 1000, you get 0.01. Yeah, and you can do the same thing. You find out the number of moles of this molecule also. Yeah, you are given the Mr. Okay, you can find out 3.5 divided by 204.1. Okay, find out what is going to be the number of moles. Okay, if you find out the number of moles, that's going to be 0.0171 mole. Okay, now, so this is going to be available in 100 cm cube. Okay. Now, the next part is, okay, you are going to add okay, HCl into it, and the resulting mixture is transferred to volumetric flask, and the solution is made up to the mark. Okay, so what is happening over here? Okay, I am going to use, okay, I will select this again. Okay, this one, which is going to be a strong, okay, which is going to be a strong base, okay, they are going to react with HCl. Okay, they are going to react with HCl, and they are going to give you, okay, NH2, okay, then double bond O, then NH S, double bond O, double bond O, O. Okay, now the O, this H will come over here. Okay, and then you will have an ACl, and you know that they say they react with 1 to 1. Okay, 1 to 1, and you see what we are getting. This is going to be actually aces. Yeah, this is aces. Okay, now what we have over here is, okay, once we get that, okay, we know that this is 0.0171 mole. Okay, and HCl, I use 0.01, just how I calculated, right? So 0.01. You see there is something in excess over there, yeah, which is going to be 1 mole will react with 1 mole, yeah. So you have the excess of this, yeah. Let's say I call this is molecule A, is here, yeah. Excess A, which is going to be 0.0171 minus 0.01 is going to be 0.0071 mole. Okay, that is extra. Okay, but they are going to form, okay, 1 mole. So if this is going to be the limiting region, so they are going to form 0.01 mole of aces. Okay, now aces is going to be actually, okay, the acid, okay, the weak acid. Okay, now what is this? Okay, this is going to be the salt of weak acid. And once I have all this, okay, I take all this, I go and put them in 250 cm3 volumetric flask, and I'm going to add water. Okay, will my number of moles change? No. Okay, you are taking everything. Yeah, so number of moles are still going to be the same. Yeah, only the concentration changes. Yeah, so I have that. Yeah, so now I need to calculate. Okay, they say pKa of aces. You see, aces is acid. Yeah, pKa is given. I want to calculate the pH of the buffer solution. Now, the pH can be calculated quite easily. Yeah, only if you understand all this. Yeah, so it can be calculated quite easily. Okay, hold on. Okay, it can be calculated quite easily. Okay, let me use this one. Okay, you can calculate them quite easily. Okay, by using this formula. Okay, pH equals to pKa. Okay, plus log, okay, Sa. Okay, salt divided by acid. Okay, and then the pKa for aces, okay, is given 6.88. You just put over there. Log, okay, concentration of the salt. Now, concentration of the salt, you see, the salt is the A. Okay, and then it's 0.0071. Okay, I'll just write down 0.0071. What is the volume? The volume is 250 cm3. So 0.25. Okay, 0.25. Okay, that's value. It's the log concentration of the salt divided by the acid. Yeah, the acid just now. Okay, you see, it's going to form 0.01 mole of the acid. Okay, so 0.01 mole divided by the same volume. Okay, 250 cm3. Okay, now what you can do, this one doesn't matter, you can cancel. Okay, so what actually you need to do is 6.88, okay, plus log. Okay, you just need to calculate 0.0071 divided by 0.01. You find that value. You will get 6.88 plus log 0.71. And that value will give you 6.73. And that is our answer, the pH. And that is going to be completed the paper. That's all, guys. So we have done this February March paper. Thank you, guys. See you. Bye.